We'll discuss about the Gauss map today, and we will consider one result on the Gauss map. Okay. Now, to consider the Gauss map, let us consider the surface path sigma from a subset U of R2 to R3. Now, the direction of the tangent plane to sigma is measured in terms of its standard unit normal n. Okay. So, curvature of sigma is rate of change of n per unit area. So now the Gauss map, which is denoted by G, it's a map from S to S2, where S is the image of sigma. Okay, so I have drawn here the Gauss map G is a map from the surface S to the unit sphere S2, where this S is the image of sigma. Okay, and this map, it sends the point sigma of uv of S to the point n of uv of the unit sphere S2. That is, this map assigns to each point sigma of uv of S the unit normal n of uv. Now we know that the orientable surfaces have well defined standard unit normal, right? The unit normal n is well defined for orientable surfaces. So we can very easily say that the Gauss map can be defined for any orientable surface. Now consider the region R subset of U. Okay, R is a region. Now the amount by which this standard unit normal n varies over the part sigma of R of the surface S is measured in terms of the area of the part of n of R of the unit sphere. Okay, so the amount by which the standard unit normal n varies over the part sigma of R of S is measured in terms of the area of the part n of R of the sphere. So we can say that the rate of change of n per unit area is approximately area of n of R divided by area of sigma of R, and we denote it by a n of R divided by a sigma of R. Okay. Now we will show that as the region R shrinks to a point, this ratio will be absolute value of the Gaussian curvature of sigma. Okay, so we are going to prove that in the next result. So what is the statement of the result now? The statement is, let sigma be sigma from U to R3 be a surface and U0 V0 be a point in U. Let delta be greater than 0 such that the closed disk R delta, which is given by the set of all UV belonging to R2, such that U minus U0 square plus V minus V0 square is less than or equal to delta square. Okay, the center U0 V0 and radius delta is contained in U. Okay, such a delta exists because we are considering sigma the open subset of R2. Okay, so in that case we will prove that the limit of a n of R delta divided by a sigma of R delta as delta goes to 0 is the absolute value of the Gaussian curvature of sigma here. Okay, so to prove this result, let us consider the definition of the area of part of the sigma. Okay, we know that it is given by a sigma of R. Okay, that is given by the surface integral of the norm of sigma u cross sigma v du dv. Okay, so if you consider a n of R delta divided by a sigma of R delta, this is equal to the integral over R delta of norm of its over n, so n u cross n v du dv divided by the integral over R delta of norm of sigma u cross sigma v du dv. Let us call this as the statement 1. Okay, now nu cross nv, if you remember the earlier statement what we have proved, if n is the standard unit normal of the surface path sigma, then we know the relation nu and nv. Nu is given by a sigma u plus b sigma v, and nv is given by c sigma u plus d sigma v. Okay, where we have the Weingarten matrix, right? Minus of this, there is F1 inverse F2. Okay, so using these relations for the numerator here, so we will get Nu cross Nv. Okay, now this is equal to A sigma U plus B sigma V cross C sigma U plus D sigma V, okay, which is equal to AD minus BC sigma U cross sigma V. Other terms will be 0 here. So this is nothing but determinant of minus F1 inverse F2 sigma U cross sigma V. So we have determinant of F2 divided by determinant of F1 sigma U cross sigma V. Okay, so this gives me the determinant of F2. What is F2? It's the matrix having the entries L, M, M, N. So it's determinant divided by, similarly for F1 we have E, F, F, G, okay, sigma U cross sigma V. Now what is this? It is L, N minus M square divided by E, G minus F square sigma U cross sigma V. If you remember the earlier result, this is an expression for the Gaussian curvature of the sigma. So it is K into sigma U cross sigma V. Okay. Now let us substitute this in statement 1 here for a norm of Nu cross Nv. So what do we get? Substituting in 1, we have A n of R delta divided by, okay, I am substituting in this statement, right? I am substituting in statement 1 here. So an of R delta divided by A sigma of R delta, that is equal to the integral over R delta of modulus of K to norm of sigma U cross sigma V du dV divided by the integral over R delta of norm of sigma U cross sigma V du dV. Now let us call this as the second statement here. Okay. Now let us consider a positive epsilon. So epsilon greater than 0 be given. Now we know that the Gaussian curvature K is a continuous function because each of these L, N, M, E, G, F, all these are continuous functions. So and E, G minus F square is not equal to 0, right? So K is a continuous function. So for this epsilon, we can find a positive delta such that modulus of K of uv minus K of u naught v naught, K is a function of uv, okay, so K of uv minus K of u naught v naught is less than epsilon if uv belong to R delta. Okay, so for positive epsilon I can find delta satisfying this. Okay, now let us use some property of the absolute value. What is that property? We know that absolute value of mod A minus mod B, this is less than or equal to modulus of A minus B for every AB belonging to R. So using that, for these two numbers here we have modulus of mod K of uv minus modulus of K of u naught v naught. Okay, this is less than epsilon if uv is in R delta. Okay, so from this statement I can write that modulus of K of u naught v naught minus epsilon is less than modulus of K of uv. I am removing this modulus sign, the bigger one. Okay, so uv, that is less than modulus of K of u naught v naught plus epsilon if uv is in R delta. Okay, so now again simplifying this, what we will do is let us multiply throughout by norm of sigma u cross sigma v. Okay, and then we will integrate over R delta here. Okay, so we'll do these two things. So we are going to get modulus of K of u naught v naught minus epsilon integral over R delta of norm of sigma u cross sigma v du dv, the first term. Okay, that is less than, okay, we are multiplying by this and integrating over R delta. So here we will be having the integral over R delta of this I have taken because it's constant there. So norm modulus of k of uv, norm of sigma u cross sigma v du dv, right, and that is less than modulus of k of u naught v naught plus epsilon, okay, into the integral or r delta of norm of sigma u cross sigma v du dv, right. So now let us divide throughout by this, all these three, right. So and we will make use of this statement here. So when I divide throughout this by, I will not be having this in the first term and this here, and it will come and sit in the denominator of the middle. So what is this stands for according to statement 2? It is nothing but this left hand side of the statement 2 here. So using statement 2, I can write that modulus of k of u naught v naught minus epsilon, right, this is less than a n of r delta divided by a sigma of r delta, and that is less than modulus of k of u naught v naught plus epsilon. Okay, so which implies that limit of a n of r delta divided by a sigma of r delta as delta approaches to 0 is equal to modulus of k. So it is the absolute value of the Gaussian curvature. Okay.